Good afternoon, ladies and gentlemen. So today we're going to be talking about the next topic in our class, and that is the Smith-Waterman algorithm. So the Smith-Waterman algorithm is an extension to the Needleman-Wunsch algorithm that we've discussed previously. So the first thing that we're going to do is, of course, recap the Needleman-Wunsch algorithm and explain why do we need to extend it in the first place. What is it that Smith-Waterman allows us to do that otherwise would be impossible with the Needleman-Wunsch algorithm? Then we're going to go over the actual algorithm itself, provide some examples, and we're going to talk about the space and time considerations in terms of the big O notation. Okay? All right. So first things first, let's do a little bit of a recap about the Needleman-Wunsch algorithm. So recap, the Needleman-Wunsch algorithm is an exhaustive algorithm. This is great because it means that we have a guarantee that a best alignment will be found if one exists, right? It's not necessarily the cheapest algorithm out there in terms of how much resources it's going to take. In fact, we know that for our problem, when we have big N queries, they're little n long and big G genome against which we're aligning, this thing is going to be O of n times O of n squared times O of G. Right? This is pretty slow because, as you recall in our example, the n is equal to 27 million. G is about 3 billion. So a loop of 27 million times 3 billion, that's going to take a while. Okay. The other thing that is important is that this is a global alignment algorithm. Right? So it is good for looking at two strings of roughly the same length and figuring out what is the best fuzzy matching alignment that you can do, right? And finally, it is an example of a divide and conquer algorithm. Right? So instead of trying to assign or trying to compare all the characters of string 1 against all the characters of string 2, we actually separate the problem into two parts and we compare the one character at a time, right? Take the best path or the best comparison score we've gotten up until this point and then move on. Okay. So Needleman-Wunsch, exhaustive, global alignment, divide and conquer algorithm. So let's talk about the algorithm for Needleman-Wunsch. Because again, the algorithm that we're talking about here, the Smith-Waterman, is going to be an extension. So let's recap what the central idea there was. So the central idea was we needed to set up and initialize our score path matrix D. Right? So for example, if we have string ATC or ATGCTA on one hand, and we have ATCC on the other hand, what we would do is, well, first of all, create the two-dimensional matrix that's going to keep the scores for the alignments that we're going to consider. Then we're going to seed the matrix. Pardon me. technical difficulties. Then we're going to seed the matrix with the so-called default alignment, essentially nothing but gaps. We're going to start at the top left corner and then introduce a series of gap scores at ever increasing severity. Right. In this particular case, we assume that the gap penalty is -3. So every time we do a gap, we do -3. Does it have to be -3? No, not really. We're just using -3 in this case for illustrative purposes. Then the match and mismatch score, let's say, is going to be +2 every time we have two characters match, and let's say -1 every time we have two characters mismatch, right? So we've set up the sort of the default path, nothing but gaps. This is not the path that we're going to end up using at the very end, but it is something that is useful for us to get started. And the reason it's useful for us to get started is because the actual meat of the algorithm is score possible alignments, picking the best at every step. But, so the way that we're going to do this is we're going to introduce a selection criteria. So if we're trying to fill in the ith cell, let's say we're looking at this cell over here, right? So the ith cell is going to be the maximum of 3 possibilities. Remember, this is a divide and conquer algorithm. So we have 3 possibilities that we are going to consider. Possibility number 1 is that we make a diagonal move, meaning we use out 1 character from each of the 2 sequences. This is a match or mismatch, right? And then we provide the score for a match or mismatch. Possibility number 2 is we make a vertical move, di-1 j plus the gap penalty. The possibility number 3 is that we make a horizontal move plus the gap penalty. Right? So to recap, we're going to consider 3 choices: diagonal move, vertical move, horizontal move. Diagonal move, A and A match, so it's a +2 from 0, which is on a diagonal, so that's a 2. The horizontal move, we're going to add a gap penalty to whatever was in the horizontal state, so that would be -6, and then vertical move is going to be -6. The maximum of those is obviously going to be 2, so the best choice for us here is actually to make a diagonal move, right? So moving on over here, the diagonal move is going to give us T and A don't match, so it's going to be -4. The vertical move is going to be -9, and the horizontal move is going to be -1, right? So the best move that we can make here is the horizontal move. That would be -1. And so on and so forth. The idea is that we keep filling out this matrix until every single step we make a locally optimal, the best choice that we can make, until we get all the way to the very bottom of the matrix, and then that will give us the best or the highest scoring path through this matrix. And then all we need to do then is follow back up to the path that took us there until we do the trace back, right? So let's go ahead and do that. So we finished the scoring alignment, and then we are going to perform traceback. By starting at the bottom right corner. And reversing our optimal moves. Okay, so excuse me. So that's essentially the central idea for the Needleman-Wunsch algorithm. It's a global alignment that divides the problem up. Instead of trying to align all the characters, you align one character at a time, and hopefully at the very end, you get an exhaustive, best possible solution. Not the best solution, but a best solution, because there's many ways. Sometimes there's more than one way to make it through the path matrix that's going to give you the same score. Okay, so that's great. Now we have a recap for the Needleman-Wunsch. What is the problem with the Needleman-Wunsch? Well, if you recall, this is the big problem that we're trying to solve. We have a large number of queries, big N. All of these queries are of, for the sake of simplicity, of the same size, little n, and we're trying to search for them in a large database of size G. If we were to implement this Needleman-Wunsch algorithm, we would need to take the first query and compare it using the Needleman-Wunsch with the first n characters of G. Because remember, this is a global alignment, so the two strings have to be essentially the same length. And I would have to move over one character and do it again, move over one character and do it again. So in this scenario, in order for us to check using fuzzy alignment whether just one of our queries is present in our subject, we would have to do in our homework assignments roughly 3 billion times, if n is equal to 36 and G is equal to 3 billion, 3 billion times 36 squared operations. That's just one query, right? And even on the fastest computer, 3 billion times 36 squared is going to take you a while, right? Now, the problem is Needleman-Wunsch is a global alignment, but what if we want to do a local alignment, right? So let's say, for the sake of argument, I have sequence 1, which is, let's say, GAT, CT, GAT, TA. And sequence 2 is ATTA, right? So just somewhat looking at it, you can see that this sequence is the same as the last 4 characters here. Now, if you were to try to compare these using the Needleman-Wunsch algorithm, you would get something that is not great. So let's actually go ahead and do that. So what I've done here is I've implemented, similar way that I've done before, a Needleman-Wunsch algorithm in an Excel spreadsheet. Right? So let's make sure that it is similar to what we were describing. So sequence 1 is GAT, CT, GATTA, right? ATTA is the same as the second sequence, and in this particular case, just to make things a little bit interesting, I made the gap penalty and the mismatch be the same. So gap penalty is -1, mismatch is -1. If I was to go through and fill out all of the elements of this matrix, Remember, in the needle and wunsch, my best alignment is here. Score of 0 is not great. If I was to reverse engineer the moves, the optimal moves that I've made, from the bottom right corner, it would be a diagonal move, another diagonal move, another diagonal move, a bunch of moves to the left, and then finally a diagonal move. So what this means for us is, the best scoring alignment that a needle and wunsch has found between these two strings is essentially to take the shorter string and stretch it out to fit the larger string, right? Rather than putting this A over here, matching it with this A, it started introducing a whole lot of gaps into the process, right? So on one hand, that shouldn't be surprising. The needle and wunsch is a global algorithm, global alignment algorithm. It's going to try to use up all the characters of string 1 against all the characters of string 2. But that's not what we want, right? In an ideal case, we want to be able to match up these characters here, ATTA, with these characters here, right? So if we could somehow do that, what would that give us? Remember, our problem is a whole bunch of queries of size n within a genome of size G. If instead of making a whole bunch of small comparisons, we could at once compare the query, sequence 2 in this particular case, with the entirety of G, right? So if this is our sequence 2, and this is our sequence 1, and we could identify that, hey, this sequence 2, the best alignment for it is somewhere over here, right? And if we could do that in one needle and wunsch-like operation, that would be great, right? Because we would have avoided doing 3 billion times 36 squared operations. So this is the rationale for the Smith-Waterman, right? So how do we take our global alignment exhaustive algorithm and make it into a local alignment algorithm? That's where Smith-Waterman comes in. So let's go back really quick to the matrix that we have created for the needle and wunsch. So one of the things that you probably have noticed is most of the values here are negative, right? Pretty significantly negative, right? The problem with the global style algorithm is once you go into the negatives, right? Once you have a lot of gaps, like we ended up introducing over here, it is very difficult to recover from that, right? It's hard to find a local alignment when you have a whole bunch of accrued debt in terms of path penalty scores that you have accumulated. And that's essentially the central observation of the Smith-Waterman extension. Let's go back to our notes. So the Smith-Waterman extension is going to essentially change this step over here. It's going to change the way that we fill out the matrix. At least that's the major change. There's going to be impacts to the other steps, but they're going to be a little bit minor. Okay, so let's talk about the actual Smith-Waterman algorithm. So Smith So it's going to be an exhaustive algorithm. We're not going to prove why it is exhaustive, but it does give us the same guarantees that the Needleman-Wunsch does. We're guaranteed to find the best solution if one exists. And the best solution in this particular case is the largest scoring based on our similarity matrix, local alignment. So this is going to be a local alignment. So essentially, it's going to be trying to find subsequences that are similar to each other rather than trying to stretch out two sequences against each other. And again, this is still going to be a divide and conquer approach. So the algorithm is as follows. We are going to change the way that we are filling out the matrix. So Dij is going to be picking from a maximum of now, instead of 3 possibilities, 4 possibilities. There's still a diagonal move, Di minus 1, J minus 1, plus whatever matches. So this is when you're using up both characters from both the strings. There's still a vertical move, Di minus 1, J plus the gap. And there's still the horizontal move, Di J minus 1 plus the gap. The only difference is we now place a floor, right? The minimum value of the path score that we can have in our matrix, right? So anytime any one of these moves results in negative values, right? So when we start accruing path score debt, we're just going to zero it out. Okay. So this is going to be our new rule. So this means that our algorithm is going to be step 1, set up and fill out the path score matrix. And seed. Now, because we have this minimum value threshold, the first column and the first row, instead of being increasingly negative numbers, are just going to be set to 0. Let's go ahead and change the color so it's easier to see. Okay. Again, in this particular case, let's say gap penalty score is, let's say -1, mismatch or match is +2, and then mismatch is -1. Okay. So step 2. So this, so far, it's essentially identical to the Needleman-Wunsch, except we have zeros instead of ever increasing negative values for the gap penalty. Then we're going to fill out the score matrix. Using our new set of rules. Right? Identical to the Needleman-Wunsch rules, only we're adding the minimum value that we can have at the table. And then once we fill out the whole thing, we are going to have to perform the traceback, and we're going to talk a little bit about that in just a second. Because the traceback is going to be a little bit different. Okay, So I've actually went ahead and done this in an Excel spreadsheet already. Let's go ahead and take a look at what it looks like. By the way, this spreadsheet will be available to you. So again, this is the sequence 1 that we had, much longer than sequence 2. This was the bad global alignments that stretched sequence 1 into the sequence 2, giving us all of these gaps in the middle instead of matching this particular character. So same thing with the Smith-Waterman, same sequence in the columns, same sequence in the rows. You'll see that I have set up the top row and top column to be all zeros, and I have filled in my my options. Now, notice in my traceback, there's now one additional option, right? So there's up, there's left, and then there's the diagonal, but then there's also the X move, right? Which means that it's no move, right? It's neither diagonal, it's neither vertical, no horizontal. That's what happens when your score goes below 0, and we have to stop making things. Now, one of the things that you'll notice is there is no sort of good scoring diagonal anymore in a local alignment. So instead of always starting from the bottom right corner, we're going to have to look in here and find the largest value in this whole matrix. So in this particular case, we got lucky and it's at the bottom right corner, but it does not have to be. So the difference in the Smith-Waterman traceback from the Needham-Wunsch traceback is instead of always starting at the bottom right corner, we're starting from the largest value and keep going. In this case, we've gone diagonal, 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 diagonal move, and then no more moves, right? Until we get to the very end. Let's actually make the gap penalty -1. Let's see if that changes it. It does not. Okay. So, and that's essentially the central idea of the Smith-Waterman algorithm. Instead of doing the traceback from the bottom right, you do the traceback from the largest value and keep doing traceback until you can trace back no more. And that is the alignment that you get. And notice the best alignment is aligning sequence 2 to the last 4 characters of sequence 1. So this is exactly what we want. Great. Let's make notes. So again, we're going to perform the trace back, but we're going to do that from the largest value in path matrix D. Okay. So great. So now we have hopefully figured out how to do an implementation of the Smith-Waterman algorithm. What does that give us? Right? Again, going back to the problem that we're trying to solve, a whole lot of queries, specifically big N of them, little n length of the queries, big G in the subject. So now if we wanted to compare the first query of all of our queries, we would need to create a Smith-Waterman matrix that is G by n characters in length, right? And then find the best trace back. Let's say it's here. And we have now identified where the best fuzzy match between the query and a portion of the subject is. Okay, great. And the reason we know it's the best is because this value over here is going to be the largest score in this whole matrix. So we're going to trace back and get to either using up all the characters in the query or not. Okay, great. So what does this mean for search time? Remember, search time for the needle and winch was O of n, because that's how many queries we have, times O of little n squared, because that's the needle and winch matrix of little n by little n. And we would have to do that O of g times. Okay, great. Now, in the Smith-Waterman, we still have big O of n queries. We have not gotten away from that. We still have 27 million queries that we have to deal with. But instead of having this term over here, for every single query, we're just going to create an little n by g matrix. Right? So, is Smith-Waterman algorithm faster than the needle and winch? Yes. By how much? O of little n. So this is not great, right? In our particular example, n is 27 million in our homework, G is 3 billion, and little n is 36, if I remember correctly. Reducing the problem size by an order of 36 is nothing to sneeze at, but it would have been nice if we could have done something about these other terms, which is exactly what we're going to do in the next lecture. Okay, so to recap, we've talked about the extension to the needle and winch called the Smith-Waterman algorithm. Smith-Waterman algorithm is designed to, instead of doing a global alignment, it's going to do a local alignment. It's going to find what is the closest subsequence of query that is present in the subject. Okay, this is still exhaustive. It's still a divide and conquer algorithm, and it is faster than the needle and winch. Whether or not it's going to be sufficiently fast enough to make the search times reasonable is debatable. It all depends on how big this little n is. Okay, next time we're going to be talking about another algorithm for fuzzy matching, basic local search alignment tool. And with that, good luck and thank you for listening.